Hello everyone. So today's topic is floating point representation. Before this, we have already seen the fixed point representation. If you have not covered that topic, I would recommend you first go through the fixed point representation and then come to the floating point representation. And also, if you want the notes of these lecture videos, then you can visit www.nargisgupta.com. There you can get all the notes topic wise, plus many previous year competitive exam papers and many university exams. So if you want all these materials, you can visit the website. So let's start with our today's topic, that is floating point representation. Before this, I would like to discuss the fixed point representation first. As we have seen in the fixed point representation, that the position of the decimal point was fixed there. We were given the numbers of the integer bit plus decimal bit, and we were supposed to follow that convention only. But here in the floating point representation, the position of the decimal point will be fixed. So let's see how do we do that. Here the first point is that all the programming languages use IEEE 754 to store floating point numbers, and that are in the 4 bytes, that is 32 bit. Binary point is not stored but fixed at a particular position, and that position is why we say this a floating point representation, because the binary point flows to the right of most significant one. That is, let's suppose the number is 1001.100. Now if I have to write it in the floating point representation, then this point will float after the most significant one, and this will become 1.001100. So this is how we do this in floating point representation. And because this point flows towards the most significant one bit, this is the reason we call it a floating point representation. The next point here says that binary point is not stored but fixed at a particular position. It means in the fixed point representation, what was happening, that if suppose the number was this, that is we have 4 integer bit and 3 decimal bit. So we were needed to store this decimal point also, position of this also, but here we will not store it as it is already fixed. And here normalization is also done, so we'll see this with an example, that how do we do the normalization in the floating point representation. Normalization is nothing but, let's suppose I have given few numbers like 0.6, 0.05, 0.12, and I have to normalize them. Then what I will do, I'll just multiply them by 100, and what are the whatever the values I'll be getting afterwards, they will be my normalized value. 6 will become 60, 0.05 will become 5, 0.12 after getting multiplied by 12 will by 100 will become 12. So this is what the normalization is. We just normalized all the values by multiplying it by 100. So we will see that how we'll achieve this normalization and floating point representation also. So this is also known as scientific notation, because let's say if the value is written like 5. In the scientific notation, we can write it as 50 into 10 and to the power 3. So this is what the scientific notation of the number is. Here, this 50 is mantissa. This 10 is base, as this number is in decimal, and this 3 is the exponent. So floating point representation is the scientific notation also, and we can represent our number in this form also. Let's see an example. Let's suppose we have given this number and we need to represent it in the scientific notation. So how we will do that? For these 7 zeros, I can write it as 10101, as this number is in binary. So the base will be 2, 2 to the power 7. And if I have to convert this into the floating point representation, which says that decimal will come after first bit, that is the first most significant bit, so it will become 10101 into 2 to the power. Here the exponent will increase as we have put it the decimal point, so it will become 2 to the power 11. Here this is the mantissa, this is base, and this is the exponent. Now let's see the another example where the number given is 0.10101 and 0000. How we will write it in the normalized form is, we will just uh, take this one before the decimal point. So it will become 1.01010000 into, as we have taken this one before the decimal point, we need to multiplied it by 2 to the power minus 1. So again here this is mantissa, this is base, and this is the exponent. This is what the normalization and floating point representation is. As we have seen that the number given was this, and we have converted it into the format where the decimal is coming after the first most significant bit. In this example also, we have done the same thing. Now let's see what is the benefit or what is the advantage of this floating point representation. Let's say I have given a value 967000000, that is the large number. So we have to store this number. But if we are following the normal convention, that is of 4 bit, that each bit we have to represent in 4 bits, then what will happen? For 9, we will write the binary equivalent of 9 is 1001. For 6, we will write 0 1 1 0. For 7, we will write 0 1 1. For this single 0, as we have to represent each number into the 4 bit, then we will write 4 zeros, and so on. Like for every 0, we will write 40 in the 4 bit convention. So how many bits we will need to store this number? As one bit is taking one number is taking 4 bits, and total 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 20. So 20 into 4, this will be 80 bits, which will be very huge. But let's say if we store this into the scientific representation or in the floating point representation, how can we do that? So we will just write it as 9 point, as the decimal should be after the most significant bit. So it will be 9.67 into 10 to the power 19. And now what we have to do, we will just convert this into the binary. Binary equivalent of 9 is 1001 4.67. We know how to convert it into the binary. We will get 1.34 here. So we will take 1 as the part of our answer, and 0.34 we will again multiply it by 2, and we will get 0.680 here, and 0 will be the part of our answer. So we can continue it and can get the answer. So for example, I am just taking 1 and 0 here. So we will write just 1 and 0 and like this. So now what is the situation? This is the mantissa, this is base, and this is the exponent. Actually, this will become 2 now. This is the base and this is our exponent. So these will be less, these bits will be less than the 80 bits. So this is the advantage of using floating point representation or scientific representation over the normal representation of the numbers. Now let's discuss the format of the 8-bit representation in the floating point numbers. So here the first bit will be the sign bit, and this will be of 1 bit only. The next we have is the biased exponent. So till now we were saying it as an exponent. Now what is this bias exponent? We will see this. This will be of 4 bit, and mantissa will be of 3 bit when we have 8 bit format. Now let's discuss what is this biased exponent and how do we get its value. So the formula of biased exponent is the actual actual exponent plus bias value. And how do we get this bias value? It is equal to 2 to the power n minus 1 minus 1, where n is the bit of biased exponent. And here we can see that the how many bits we have in the bias exponent, that is 4 bits. So it will be 2 to the power 4 minus 1, which is equal to 7. So bias value here will be 7. Now let's see it with an example. Let's suppose we have given 0.12 and we have to represent it in the floating point numbers of 8-bit format. So first we will convert this 0.12 into the binary, and for that what we do, we need to multiply it by 2. So we will get 0.24. Again we will multiply 0.24 with 2, we will get 0.48. Now we need to multiply 0.48 by 2, we will get 0.96. We will multiply 0.96 by 2 and we will get 1.92. We will multiply now 0.92 by 2 and we will get 1.68. 0.68 multiplied by 2, we will get 1.76. Now as we are getting 1 repeatedly, we will stop the conversion now and we can write it as 0.000111 as we we were getting 0 here, we were getting 0 here, 0, 1, 1 and 1. And I have explained this in my previous video that we write it from upward to downward. So this will be the binary equivalent of 0.12. Now let's convert it into the normalized form. So what we have to do, the point will float after the first most significant bit or the first one bit. So we will write it as 1.11 and 2 to the power minus 4 as the decimal is getting shifted. Now what we need to calculate, we need to calculate biased exponent. So the actual value here is minus 4 and the bias value in the 8-bit format we have calculated is 7. So we will add it here and plus minus will be minus with the positive sign. So we will get 3 here. And now we can represent it in the format like this. As this number is positive, so the sign bit will be 0. If it would be negative, then the sign bit will be negative. Then the bits which we are getting in the Mantisa is 0.11. So, but we have to represent it in 4-bit. We will add two zeros and we will write it as 0011. We don't write this 0.1 because this is already fixed. It is understood by the system that if we have 11 here, then the actual number will be 11. And let's say if we write in the Mantisa 0100, so the system will automatically treat it as a 1.0100 because as in the floating point representation, it is fixed that there will be the 1 before the decimal. Okay, and here as we are getting 3, so in the binary we write 3 as 110, so we will write it. So this is the sign, this is Mantisa, and this is biased exponent. So this is how we represent numbers in the floating point representation. In the next video, we will see the single precision and the double precision format.